No. Hola.
Wait, I need to. Sí. ¿Cómo es el canal? Ya estás transmitiendo.
Sí, 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 hay que ver eso. Yo creo que eso está fuerte.
Should I say something?
We start 1 second. Okay, so I think we can start. So welcome to the first session of today. So it's our pleasure today to introduce Professor Fernanda Duarte. So she is an expert in machine learning potential, but also simulation of organic chemistry reactions, right? And indeed, you work in many fields, so probably we will later do a kind of overview, I don't know.
Yeah.
And she's from the University of Oxford. And okay, so the stage is yours. Thank you very much for coming, Fernanda.
Thank you. Good morning, everyone. Thank you very much for the invitation to this summer school and to everyone that has been involved in the organization. It's a great kind of setup of the speaker that they put together, but also the venue is amazing. So, and I hope that you are enjoying as much as I do. And before starting, I would just like to introduce myself and the group. As you know, we'll be doing a tutorial later today. And so I will just like to start introducing the people that is in our team. So we are based at the University of Oxford in the Department of Chemistry. We're a very diverse group. both instead of the science that we do, but also nationalities and background. And today is with us, you will see, is Veronica and Hangwen are there, and they will be teaching you later everything about MLP train. That is a package that we will use today. So there are many different people in the group, and some of them are doing machine learning potential, and some others are doing other things, because as a group, we're very much interested in a broad range of topics, and those are mostly focused on chemical reactivity. So we're very much interested in understanding how bonds break and form from very small molecules, those ones, where we explore the effect of the strain in reactivity, but also in larger systems such as supramolecular systems and biomolecules. And I know that many of you are, is that okay?
Yeah, it's okay.
Many of you are interested in biomodeling. Maybe the aspect that we'll be teaching today, machine learning, is not yet there, but our motivation has been building into moving in those areas. So as we develop new methodologies for a small system, can we push those methodologies to be applied into larger, increasingly large and more complex chemistry? And the motivation of exploring this larger system has been the one that has driven us to explore and to develop a different software. So I think, is it working? That is frozen. Yeah. Oh yeah. Yes, now we're back. So because we want to explore different system, and in a, like the science is what motivates us, and the kind of code development has come as a necessity for us. We need to do the work in a more efficient manner. We need to automate some of the processes that we do to be able to explore the science. And that has been the main motivation for us to develop some of the code that the group has put out there. Some of them related to reaction automation, exploration, supramolecular chemistry, as I say, is an important area of research in our group. And more recently, machine learning potentials. And there is amazing people that have developed these many tools out there. And in many cases, we have benefited from the development in the theory there, and we have been able to use that and combine that in automated approaches and make our life and hopefully your life easier when you are exploring chemical reactivity. An important part of the motivation that the way that we do science in the group also is maybe summarized in the words of Charles Colson. He was a professor in theoretical chemistry in Oxford, a leading person in theoretical chemistry. And in the 1959, in a conference, he was seeing how the community was developing from theoretical chemistry, very kind of theory approach focused, to more applications. So it's, in this conference at the end, he gave a speech at the end of the dinner, and then he said, kind of, in this meeting has been kind of an amazing place, as always, very, very nice words about the theoretical developments that were done, but also the experimental applications that were coming, very new at that time. So he did summarize in his speech, for example, that applications to benzene were being developed, a lot of spectroscopy approaches for very, very small molecules. So at that time, applications were still very fundamental. We take them for granted, but was very, very revolutionary that people that was coming, like 30 years after EuChemS was developed, we were seeing those applications. And he did emphasize the importance of keeping the two communities together. So we have seen a wide range of applications in this conference, and maybe the communities will become separated. They will go different ways. The ab initionists that will really care about the kind of more accurate approximations to solve the Schrödinger equation, and also the posteriorists. Maybe they will divide in different paths, but hopefully they will still be connected because there was much need for that. And many years have passed since his speech, and now the posteriorists are not looking anymore maybe to benzene or very small molecules. They're looking at very much a bigger system. We feel kind of posteriorists in our group as well, but the challenges are still there. We still need to talk to the ab initionists, and then need to talk to us. And I think that the combination with experimentalists in this stage made his words very timely, even though they have been kind of more than half a century ago. So the challenges are just, as we develop more things, the threshold for us, kind of what we expect of ourselves, is much higher as a community. And I think that that is great to see, because we have achieved quite a lot as computational chemists. If you think about what was developed in the early 2000s, maybe very far away for many of you. Maybe for me, it's not too much. It's like, okay, I was thinking kind of about a study at that time, but 2004, I started my undergrad, so it doesn't feel so far, but still, when I started studies on PhD around 2010, 2008, 2010, the field kind of when I was looking at papers, I remember as a student, any paper that was before 2000 for me felt very old. Maybe for you, anything that is before 2020 feel very old already. But still, anything that I was reading, like papers around 2010, and the papers coming from the early 2000 was very much MD, very well-established techniques. And you have seen yesterday, you saw all the theory behind that, developed in the 70s. And then from the computational EuChemS side, most of the papers were very much B3 lead, very popular at that time. And some of the early 1990s, 2000 were kind of hard to fog with some MP2 calculation, everything in gas phase. That was more or less the literature that I was reading related to DFT, organic chemistry applications. And it's impressive because many of them kind of hard to fog computations that were done very early on by Ken Houck, for example. Many of the kind of conclusions that I made in those works are still relevant. Many of the models that we use in organic chemistry come from these models. So in that aspect, they were given insights very early on, and that is amazing. But as we move on, we also want to have more numbers. And we know that those methodologies are not perfect. And in that motivation, people have developed increasingly more accurate methodologies so we can get insights and also numbers now. So if you think about what you have available today as a student doing quantum chemistry is very, very broad instead of the type of software that you have, but also the methodologies that you can afford. I don't think that you will be running calculation for a publication with hard to fog anymore. And even some MP2 gas phase will pick kind of, not so much. It's very obvious to you that you will do a single point with DLPNO coupled cluster, which before was not there yet. It was just coupled cluster. The approximation was not there, which means that everything was super expensive. So now we take for granted this wide range of log scores, methodologies also developed by Grimm. All these things, we have a kind of too many options sometimes to choose of what we want. And it's very much where our expertise as a chemist come, like what is the accuracy that we need for the problem that we have at hand. And what is important to emphasize that in all cases, what we have is a system, can be a small, can be large. We need to translate that system in a way that the computer will know. For example, basis set. We compute, we have a framework, a black box that we call ConSham DFT, that we call a kind of wave function methods. And then those methodologies will give us energies and forces. And from that, we can do ab initio and D, or we can just do spectroscopy, or different observables can come from those analyses. And very important, these force fields that were developed in the 70s are still very strong. And you saw yesterday the theory behind that, but also the many applications that are still being done with those methodologies. But again, there are challenges as we move forward. There are also things that we want to explore that we couldn't before. And the challenges relate to a few aspects. One of them is electronic structure methods. We have this wide range of different methods now, but we need even higher accuracy and more efficiency sometimes. Many of the methods are not very robust, have a SCF converter issues and so on. So there are practical, some fundamental aspects that people working in the Q and the more theoretical aspect are still very interested on. And that raised the point of how important is those ab initialists that we think are doing just theory in the small molecules. Their contributions are still very important because one of the key challenges are related to electronic structure methods. They are the bottleneck, even when we do machine learning potential, as I will show you later. The other one is chemical accuracy. We chemists want to compute things that have kind of small energy differences. And sometimes it's very strange for people working on machine learning potentials in material to understand why we need such accuracy. If we think about hard to fog DFT, those methodologies give us 99.9% of the energy correct. And this is tiny error. It's like the balanced electrons that we need to compute very, very accurately to describe the chemistry that we want. Okay, so we are kind of subtracting big numbers. And even though the error between them is kind of small percentage-wise, kilocalorie per mole for us is huge. And one of the examples to illustrate that is enantioselectivity. If you think about, well, different type of selectivity, but enantioselectivity or regioselectivity relied in many small energy differences. For example, we have two molecules, R and S. One is the good drug, the other one is the bad one. Thalidomide is maybe one of the extreme examples when one was the drug that wanted to be used by pregnant women. The second one was recognized to be formed in the body and had very kind of deadly effects. So we really need to separate those molecules, and the energy difference between those molecules, what leads us to each of them is very small. So the energy difference between them is zero because they are enantiomers, but the pathway that leads to that are diastereoisomers, and energy difference between them often right between 3 kilocalories plus minus 2-3 kilocalories per mole. Okay, so the accuracy of our method has to be in the 1-2 kilocalories per mole, more or less, error. Enantioselectivity benefit a lot from error cancellation. That is something that you don't have in regioselectivity, for example, or chemioselectivity, where this error cancellation doesn't hold, and sometimes even trickier. So even though this is a very challenging problem, sometimes enantioselectivity is the easiest for a computational chemist to address compared to regio and chemioselectivity. So getting chemical accuracy is still very difficult as we move into larger and larger systems. Other challenges is how we automate processes. We used to draw in undergrad these kind of energy profiles where maybe you did some Gaussian calculation, or currently ORCA, you draw your molecule, starting material, your product, and then you have a good intuition about what your transition state is. And that is great that you can do manually, but if you want to do hundreds of reactions, that manual work becomes very challenging. And we have been doing, as many others in the field, work in the area of automation of reaction pathways. They're using quite a lot of graph representation models to either using information of reactant and products, or all information of reactant to explore the energy surface. And finally, some of the other challenges are related to how we include solvent effects, entropy, and dynamics. That is something that we take for granted with classical MD models. They are impressively accurate in that aspect, but they do not account for reactivity. So introducing accurate ways of computing entropy, thermal effects in QM calculations is still very difficult. Because then you need to solve the Schrödinger equation, or the approximation of the Schrödinger equation, for all these electrons around that. So this is more or less a summary of things that we have, and we use quite commonly in our group to explore reactivity. We use a lot of QM, mostly DFT methodologies, some of the MP2 with MP2 and the DLPNO coupled cluster, hybrid approaches, which you have seen also the theory behind, and molecular dynamics. Each of them with their pluses and minuses. Many times we do dynamics, and dynamics is way more important in proteins, I will say, than having accurate kind of QM method. So if your geometry is wrong, or if you don't account for dynamics, doesn't matter that you have a very fancy DLPNO energy calculation if your conformer is wrong, for example. So those are things that they have pluses and minuses. QM is kind of the gold standard instead of electron extractor methods that you can use, but doesn't consider explicit solvent. The number of atoms is quite limited, and it's a static model. Okay, give you one energy, right, and then sample of models that you will have. If you will move into dynamic and molecular dynamics, you have the dynamics very cheaply, which are classical potentials, but reactivity is not possible by default. There are some ways to bypass that, but they are still kind of specific approaches for that. You can go for very large system, but again, it's the reactivity that is very important for us that we don't have there. And even the accuracy, kind of getting numbers out of there is very difficult. So a solution to that kind of come with machine learning. And in the different ways, you have seen machine learning in many different flavors. And the idea of a machine learning model is that you have this black box that is trained with data, and then you can have in our case, a representation, and then you can get an observable. So with machine learning potential, we have a geometry, And that geometry, we put that in this box and we give us energies and forces, okay? In some cases, what your ML model is doing is giving you observables directly, kind of, I don't know, E values, for example, or by putting smiles here. So there are different ways to represent molecules, and then what are the observables are different. But the key is that you need to train a model first to design this black box, and for that you need data. So a very graphical representation of what a machine learning potential is maybe thinking and going back to classical force fields. So the force fields, what they try to do is provide you an energy that is composed by different contributions. So for example, here we have a bonding term and non-bonding term. In the bonding, we have, we usually use harmonic approximations. And then those when you saw that in the first day, when looking at MD simulations. And if you see it's a very, very simple representation. So the energy contribution from a bond will come from this equation that has only two fixed parameters, the force constant and the reference distance. Those are the only two parameters that you have to fit. So you optimize those parameters until you can reproduce the kind of true kind of a dissociation curve. Okay, so two simple parameters that you tune based on data, and then you have different approaches that force field have been developed. But they're restricted. So these are, for example, in this case, a harmonic function is very simple, but doesn't allow you to dissociate. So you cannot break bonds at all, even if you increase the energy. But still, they give you only two parameters. You can have empirical functions that allow you to break bonds, so they can have this shape, but you have to introduce more parameters, 3 or 4 parameters in total. What MLPs try to do is say, let's start, we don't have knowledge of the system, but try to get energies of points that we know. Maybe we know the reference, the kind of the minimum here. I can maybe elongate a bit the bond, stretch a bit the bond, and I can compute energy of those points there. And I try to fit that function, allowing full freedom. Okay, give me any energy, like mathematical form that will fit these 5 points. And the first one maybe is not great, allow you to describe the system at the minimum, but as soon as you start to distort that more, this function will divert and will give you crazy energies. Say, okay, it's not great, but maybe I can add more points, and now I can have something that will fit better. And that is the way that machine learning potentials will work. I give full freedom to my system to have any kind of mathematical energy form in order to describe the data that I have provided. Of course, there is a balance, because as you start to add more data, you may end having to kind of overfit to a specific system. So you want to have something general that allow you to interpolate, but also extrapolate beyond the points that you have. And that is always the compromise that you have. But in both cases, what you want to fit is something that will kind of based on the knowledge that you have provided to your function. So if we explain this in a more schematic representation, will be, we have the coordinates here. In the same way that we add coordinates to a Gaussian calculation or to a ORCA calculations, you have to convert those into a representation. Often we use basis set. In this case, we use a different representation. And then we use this task that can be a regression, but also can be a much more expensive and fancy ML model. And that will give you energies and forces. Okay, so the fitting process here is done. This is a very simplified way of fitting, but can be many different frameworks, architectures to do that. In all cases, you need this reference data. And what you get on there is a sum of energies. So it's in your case, you have a different atoms, and your total energy will be a sum of local atomic energies. Okay, and all the MLPs that are around there are based in this locality assumption. Okay, that your system can be described as a sum of atomic energies, which from a quantum mechanical point of view doesn't make sense, because there are no operators related to atoms. You only have a molecule. An atom does not exist in a molecule. But in this case, this assumption is key for the system to be able to kind of provide something meaningful to compute. And this energy is a function of the atomic position, but also of the chemical element. Okay, so you have to tell the ML model, okay, these are the elements that I'm describing, carbon, nitrogen, oxygen. And that is the reason why you cannot use an ML model that doesn't have the atom type that you want, because it has to have a reference energy value to start with. Okay? But the locality assumption is key for everything that we do. There are many approximations there, many limitations, but also allow you to do a kind of practically use and implement those models that otherwise will not be possible. And MLPs, as you have heard, are becoming increasingly popular. And the promise, they say, is that here you have the force fields that have been developed for a long time. Here you have ab initio MD. Many of you maybe are using those approaches. And now you have MLPs, which aim to be kind of much more accurate than the force field. The computational cost is higher, but they try to be as close as possible to classical force fields. Maybe that is not true today. We are not kind of getting kind of as close as we would like to classical force field, but the hope is that we will move in that direction, that we will reach accuracy that can be as the one that we use with ab initio MD or even higher. Okay, for those of you doing ab initio MD today, you often have to rely on GGA kind of functional, something that is kind of relatively cheap DFT wise, and often you cannot do ab initio MD with anything that is kind of meta GGA or even the double hybrids or anything that is too expensive. So with MLP, the idea is that you can go to higher accuracy if you want, couple cluster, and be as efficient as force field. Maybe it's not the case today. We are kind of in between, but the hope is that. And people developing machine learning potentials have been working on this for very long time, but has been only the last 7 years, more or less, that people have started to use them for describing chemical models. Please feel free to ask any question that you have in between. Yeah, don't wait until then.
Yeah, sorry, the energy that we can obtain as output from the machine learning potential is comparable to the SCF energy from GAP.
Yeah, so the energy that we get there, the sum of the energy will be as accurate as the reference model that we have.
Okay.
Okay, so these energies may come from semi-empirical methods, can come from XCB, they can come from couple cluster. So it's like the person training the model that will decide, this is the accuracy that I need. The ML model will just learn to fit to what you give them. And that is very important when the benchmark and having a bit of background on electronic structure methods really helps.
Okay.
Yeah. Any other question? Yeah, feel free to interrupt me in between, because I don't think that I can go continuously an hour and a half without any break. And about the data, that is a very important point. What do we use for training? And what is available out there? Data is something that we take for granted. Often with ML models, sometimes many students will come to our group saying, I want to join the group because I want to do ML. And the ML aspect actually is the easy one. If you go to Coursera or any of the online courses, they give you the data and then you do the ML. And actually with the data, then you can train and get the ML model to work very easily in a day or in a week, kind of at most. But often the issue is data, in chemistry in particular. So we'll start just summarizing. Maybe all of you know quite a lot of electronic structure methods, but we often organize DFT functionals based on what is called the Jacob ladder, forward by Perdue in 2000. And the idea of Perdue, he's a very much a DFT person, very a physics approach, like trying to build DFT functions from first principles. And the idea of him was that if we develop functionals that are kind of accurate, built by kind of from the beginning with the thought of accuracy to fulfill physical constraint, then we should be able to build on something that will be kind of, as we build more kind of ingredients in our DFT function, things will get better. Okay, so we know that, for example, LDA is not great, it's just based on the density of the system. But if you introduce the gradient of the density, then we have the GGA functionals, then the description will be way better. And this is something that we see the errors, for example, going from LDA to GDA is like, it's substantial. Like it can be 50, 100 kilocalorie like difference in atomization energies. It's kind of significant. Just including a bit of more information of the energy of the density landscape. If we introduce kind of the second derivative of the density, we have the meta GDAs. And also we have these hybrid approaches where we have a bit of Hartree fog, a bit of the DFT there. As we increase in accuracy, we also increase in computational cost. But the hope is that with this functional and properly developed, as we include more ingredients, we should improve. Yeah? That is not always true. It's true because many functions have too many parameters, but that is the hope. Okay. And why I'm including this? Because this will determine the kind of the reference data that we will use. Okay. Maybe you're doing just material. I say just kind of as it is easy. Materials have their own challenges, but in many cases, LDAs kind of is good enough to describe periodic systems. Kind of with a wave function based DFT, those are very accurate for the chemistry that you want to explore there. But if you want to explore chemical reactivity, you know that you have to do at least a GGA. And if you want to have quantitative accuracy with activation energies, you must go into a hybrid that will include some Hartree fog component. Okay. And that is because Hartree fog is exact in the exchange part. It doesn't include the correlation, but has a exchange accurately, while DFT doesn't account that for directly. So we know that to get geometries, we need GGA, and that is our rule of thumb in the group. GGA most of the time for organic molecules give us good geometries, and then we can do a single point that will be either a meta or a hybrid ones. Okay. And then if we have some type of contribution from other determinants, double hybrid sometimes is very useful, where you have just a slightly higher correlation, but you don't need to have a fully multi-determinant wave function, but still it's like a system that will have some small contribution that is important. But each of those calculations is very expensive, okay? So even though a single point DFT calculation takes you a few seconds today, if you want to do that in larger systems, solvated, still a single point maybe is not too much, it's 2 hours, around 3 maximum, but then you have to do hundreds of them. And that starts to be very time consuming. So if you think about an ab initio MD with a small system, okay, it's a few weeks, you can wait for that. But if you want to be a solvated system with that level of theory that is not too bad, then you have to wait for years. And that is where the benefit of doing MLPs come from, okay? You train in those expensive molecules, so you have to do these single point values, but then later you can train a model that can allow you to do dynamics on time. So hundreds of evaluations using a model that is not taking care of electrons at any time. Okay, but yeah, where is the data coming from? Okay, and the data is often, as I say, DFT. Some people is using ab initio MD, and that has been the common training in many of the machine learning potentials, but it's something that sometimes is hidden in the model. Some people have more access to computer times, and there are many data sets now out there that have energies and forces that we could, in principle, use for training. But very important to consider what I will need for the model that I want to train. Apart from data, once we have data that we know that we need for our model, we need to think about the representations. We cannot just give X, Y, Z coordinates. That doesn't work for computational chemistry. Even in QM, we need to convert our system to something that fulfills physical symmetries. Okay, that is very important. Even in when you think about basis set, there are systems that doesn't matter if your water molecule is rotated, if you translate your water molecule, the energy of that molecule should be the same. Okay, and that is very important in any type of application in kind of quantum chemistry and both classical and quantum models. So you want to rotate your system and the energies should remain the same. If you have an inversion point, if you invert the molecule, the energy should remain the same. If you translate that, it should also be consistent. And that is the reason that XYZ coordinates are not a good input feature, okay? Because otherwise you provide a different reference point and then the energies will change, and that should not be the case. And there are different, you have seen maybe some MLPs that include this symmetry group. So they try to retain very important rotation and translations, okay? And when you think about architectures and ways to represent, there are different frameworks. So you can have a machine learning model. For example, you provide an input and that will give you energies. In some cases, you have invariants. So invariance MLPs, where you have this input is rotated, and then the energy should be the same, okay? And nothing happened with the internal features. And there are some new models like equivariance, I mean, they have been there for a couple of years, but they come second generation type, where you have, but when you rotate your molecules, the internal features also rotate. So if you have a vector, that vector would also rotate. Or the symmetry operations that you do in your input, you will do in your internal features, okay? And that gives you some extra information and more flexibility in the model. Okay, so EuChemS is one of the kind of key and more famous approaches that will do that. What you don't really want is something that you rotate your input and that will change the energy, okay? That is not. And the basic ones will be you rotate and then the system will give you the same energy. Okay, so that is invariance. And the equivariance that the vectors or the other internal features will also be modified. And that means that you can also sometimes use fewer data points, okay? That is the main benefits of many of the equivariance models. And how you describe the system here is there have been two popular approaches. They are kind of the traditional ones where you have the atom center symmetry function and the smooth overlap of atomic position. One is more the kind of the standard way that maybe we'll describe electrons, even in a molecule where you have the radial and angular distribution, very much inspired by spherical harmonics. And then the other one is based on the density. In all cases, you want to describe your atom given the position of all the other ones around. And you provide some radial information and some angular information that will have a cutoff. Okay. In most cases, so in the radial distribution, you try to see around your atoms instead of pairs and then many variable order representations, or instead of a density around your system. Okay. And in those cases, that will be dependent of the atom type that you have. And that is very important why the MLP will be, if it was trained for oxygen, nitrogen, sulfur, will not work for, I don't know, phosphorus, for example, because there are some definitions put early on in the description. In the same way that we do basis set. Some basis set have parameters for the whole periodic table, some other don't. Okay, and then you can just not use them. And those, the way that we describe the system is now becoming more connected to the way that we do the ML model. Because in the early models, you have these features at the beginning, and those don't change, okay? This is the way that I describe my system, and this is taken as it is by the model, and that gives you energies. We'll see that the new message parsing neural networks, they try to kind of update these features as they are being trained. And that leads us to the other aspect, that is the architecture. Do you have a question? No? Okay. Yeah.
One question. So when we're doing the machine learning model training, we usually expect the representation of the molecules to have the same length or the same number of features.
Yeah.
So in the case of your representation for these atomic potentials, how do you deal with the fact that you might have molecules of different sizes? How do you make sure that you encode them into a fixed length vector?
Yeah, so in general, with the classical ML models, like the linear regression models and so on, that was very important. Like if you just use data, they will just add with zeros. But now with the new models, you can kind of make them more flexible to expand, to train with different data sets. And you will see later that the models that we use allow you to have training sets that are at different sizes, and they can be kind of combined at the very end. So those are the new representations. But initially it was very kind of as if you think in data-driven ML, that used to be the case, that we just have kind of full of zeros to just make the length aggregate length. In those cases, you can, in these cases, you will see later that you need to maybe do that kind of average. some of the descriptions to allow for this generalization, but allow you to go for different data sets. So most of the systems that are trained now allow you to test in systems that have not been seen and are much larger or smaller than the one that we use for training. Yeah.
And also for the calculation of these representations, I'm guessing that you have to use the optimized structures already, right? Or...
Not necessarily. So sometimes you want in a materials machine learning model, what people used to do is just hit a lot the system. So you have a one starting molecule and then you hit and try to sample the energy landscape because you want to show the system high energy points.
Mm-hmm.
If you have something very optimized, it's like when I was showing the 2D energy profile, you can describe very easily the minima, but then as soon as you go slightly away, the system will know nothing about that. So maybe the shape of that potential is completely different to the physical one that you have. And for that reason, you have to give the energy points that are away. What we do often is to do random displacement. So just a displacement of like, I don't know, 0.2 or like a few kind of point angstrom type, and that allows you already to have this distortion, and you add those single point energies there. So you have an optimized geometry at the beginning, but then you can distort the system a bit. And that is very important. In the case of molecules, we did try initially to hit the system to get high energy points. And actually that was not a very efficient way to do that for us because we're sampling just crazy parts of the energy landscape that we will never explore for the chemistry that we were doing. So it's always a balance because you can say, I want to explore everything, but that will mean a model that we need many parameters. So we need to know a lot of everything. So it will take time for training. And that is I will show later how we do for chemical reactions, where the energy landscape that we have is kind of, we need to go for high energy regions, but they are not kind of all the potential combination of reactions that we will have. And so that is important to have energies are away from the minimum. Any other question? Yeah.
So it's question actually. What will is this the same case for if you are planning to try model all the proteins, like trying the protein model, where the molecules are huge and all the crystal structures available of a single protein may not be of same length, or some part of domains are missing, or 2 chains are there, 3 chains are there. So how to approach that one? Should we need the other chains or
Yeah. So the approach with the MLPs has been kind of the locality aspect is back to that. It's very important. And what you can do is in the same way that force fields, like for example, classical force fields, they were not trained in kind of full proteins. They say, okay, we'll build amino acids type. We have these building blocks, we will parameterize them. And if the assumption is that if we do something accurate at the beginning with the small models, the combination of them should give you something that is accurate, provided that we have these covalent interactions and then the non-covalent interactions. In the same way we do that here. So MLPs, some of them have been tested now in big molecules. There are a few models out there, and the principle for them was also building from a small fragment. And that means that when you apply them, you can test them in a lysozyme, but also in a very big protein. Okay, and then the length aspect is gone, because you are building from a very kind of a small system in the same way that we do classical force field. We don't parameterize whole proteins. We do building blocks. And in this case, even the atom center aspect gives you an atom in a molecule. If you ever describe well these environments, then anything that have those environments should be described properly.
Any example of the current models that you're telling?
Yeah, so there is Annie has been tested for proteins already, but most of them has been so far a gas phase system and dynamics mostly. So going into solving and the main challenge with proteins is to compete with the classical force field. Instead of the length, you can do microsecond MD simulations with the classical force field. And with proteins, they have become very, very good. They are extremely good. Maybe the RNA is not so good and has been a slower approach, but if I'm thinking about dynamics, I will still go for the classical force field because the MLPs are still very slow to iterate. What is the difference in German? well, Jatenko in Luxembourg and others that I have cited here, Mueller, for example, they have shown models they can do small proteins. There, I can give you some reference later. But in all these cases, it's difficult to claim that we will compete. They're just very impressive approaches that how far we have gone. And the idea will be that we can compete with the efficiency of the classical force field. Okay, because they're much more accurate, but the efficiency is not comparable. Any other? Yeah, so some of the models, the early models and most of the most popular maybe are the Beller-Parinello neural network and the ANI potential developed by Adrian Royberg and Alexander in the US. They were kind of the pioneers in this field. And the main idea was to have this atomic representation of radial and angular representation and fit that handcrafted like a fixed descriptors into a neural network. Okay, the neural network were often very large and they needed quite a lot of data. You will see later we will be using different approaches to this standard neural network, and the idea is to make the training more efficient. So the training data, they require quite a lot of training data, but it was very nice to have this transferability early on in the model. So, and if, for example, the first one, it was carbon, nitrogen, oxygen, hydrogen, and then anything that will have those atoms, you could describe them using the potential. Okay? That was something that was already very, very nice. But then you have to, every time that you want to add, let's say sulfur, you have to train the whole neural network again. Okay, there was no way to bypass that. And they needed to, I mean, they were kind of the people that have the computational power to do that. And that was amazing. And now they have been increasing that with different level of theory. But again, every time that you want to add something, you have to retrain the whole net. There were other approaches that were much more system specific. That was the kernel-based approach pioneered by Gabor Tran in Cambridge. And the idea is very simply you have this density-based sub-descriptor, and you compare the density of your system. So this atomic system here, I'm inputting a data, and then I have data in my training set. So how similar is the energy, similar is this molecule to anything that I have in my training set? And I say, okay, this similarity is similar to that one and that one. And based on that, I can give an energy. So I know the energy of A and B, and maybe my configuration is something in between A and B, then the energy should be a combination of those. And that is the kernel-based approach where you have this similarity measure. If it's identical, we'll have the same energy. If it's completely different, maybe we'll struggle to identify what to compare to. But the idea is that you train a model that have this similarity, something that is relatively similar, so the system can interpolate and extrapolate a bit there. Training was what more efficient, but the transferability there was an issue early on. There have been the more recent developments has been two frameworks. One is a very classical approach to that. That is, one is the atomic cluster expansion, where you have a kind of many body order representation, very similar to a force field, but they have some very nice tricks in order to make this computationally feasible. Okay, because in principle you can describe any system in this many body order representation, but you will see that get kind of increasingly expensive as you go to more order. But you can have some, because you have cutoff around that, and some mathematical tricks allow you to do this more efficiently. It's much more simple to train that standard neural network, but it's less flexible to anything that we have today, like maze or the other things that we'll discuss later. And the idea, again, we have a cutoff, and each atom center, for example, this carbon here, is described with a radius around that. And these are some of the many parameters that you will be playing around this afternoon. And many of the parameters that you choose, which is the radius that you use, that will be very much based on the chemistry that you want to explore. And the other type of architectures that are kind of the state of the art maybe are this message passing neural network, where you have your system is describing in both cases it's a graph neural network, so it's a graph representation of your system. you have a vector communicating between each of the atoms. But the idea of this one is that the features are they are called end-to-end learned. So you don't provide a static feature as an input and that gives you the energy. As you go through the message passing layers, you kind of evolve that representation. Okay, and that is great because then you can have a bit of a kind of long range, many body order kind of effect without explicitly going for this kind of 3-4 body representation. And one of these approaches is MACE, that is developed by the Duarte groups in Cambridge and has and many other contributors here. The ideas are kind of with the standard ACE, you have this fixed radius, but with the kind of MACE model, it has just 2 extra layers, but that allow you to start this input representation. And as you go into the different ones, well, they pass 1 layer, then you could provide information of what is connected to that. So the representation of the features of your system are evolving as you go through the neural network. Okay? In principle, you could include more layers, but as you include more layers, become increasingly expensive. And then now going into reactivity, this is what we wanted to do initially. So we started to use machine learning potentials for chemical reactions in 2019 was the first attempt that we did with this kernel-based approach. Was a gap at that time that we were using. And we saw kind of the first test was like trying to mimic what material people were doing, and we were not very successful. So it was a lot of learning what needs to be done differently. And then the field has been moving on. So when we started working like 2018, then 2020, the first work came with a neural network doing chemical reactivity. And you can see these were all kind of more or less kind of very Parinello neural network, the classical one. And the number of configurations that you needed for training were significant. And more importantly, all these representations were coming from ab initio MD simulation. So first you had to do ab initio MD, take those systems and then train the model. And doing ab initio MD is already very expensive. So it was like something very expensive to train a model that will be doing the same that you already did with your model. And so it was just something that for us was non-feasible. Even when we were considering any models, any time that we needed to add something else was just too expensive for any computer power that we had at that time, especially because they rely quite a lot in GPUs. And then people started to do active learning, which we'll discuss later. And that was a key aspect of kind of learning as you use the potential and adding new data, because that allowed us to go from 300,000 to 30,000. So really did decrease by an order of magnitude the amount of training data that you needed through this active learning configuration. But it still was very, very expensive. And our motivation was to try to do something for organic molecules and to introduce solvents. So trying to find efficient and cheap ways that we can do MLPs, provided we don't have this very fancy computational power to do ab initio MD or to train this very big neural network. So, and that was the main motivation for us to start working in this area. So I think that maybe we can take a few minutes break, and I will start to go for the work that we have been doing specific in this area. Will be connected a bit more to the tutorial that we will do today. So maybe 3-5 minutes break. 5 minutes. Por ahora mucha gente que hace I saw some like one of the so I was like, maybe that's. Yeah, so. Yeah, exactly. So 12 there. Yeah, they used to.
I don't know a lot about how to get started.
Yeah.
I don't know where to keep it right, but like I never like they're very old brain, and that's why it's very like very good. It's all as you go, it gets easier. And like so outside. Yes. As to be in a comfortable and
You become your comfort zone. Yeah.
And you get, when you fail, and you try again, and you have to start,
The one that the voice
Your mind is.
and these are like the very early ones, they don't know what choice. They don't just know that the system has this environment. Then you only just change the relax.
So, to get,
Yeah. So they so one half is and analysis. And you will see the second analysis, but there is a difference between because they are not just average. You cannot differentiate, but it's higher for them. But you will have a stereotype that are wrong. Also the captains that way. But that's the thing that happen with just but you need to provide that. Yeah, so you get yeah. There's that try
Yeah.
Maybe by
I was so enthusiastic.
it's people everything legally.
Because you know, I play with my hands.
But they also ask.
Like, of course.
Okay, so then we continue with it.
Okay, we will continue. So the second part is mostly about the work that we have been doing as a team. And this is just summarized here in the tool that we have called MLP Train. Yeah, and this has been possible because many groups out there have been developing being these kind of QM approaches or ML architecture. So we have benefited quite a lot from a lot of work from different groups that make the code and the software available openly to us. And this has also been evolving as new architectures come into play. So the idea was for us, because we used to do kind of QM calculations, that was ORCA, Gaussian, XTB, and for that we developed AutoDE early on to compute automate reaction pathway search. So we tried to do that general for this software and a few others. And then when we started to use MLP, there were other type of softwares that were just related to MLPs. We started with GAP and then ACE and MACE. NICU, we did implement at some point, but mostly we are using MACE today. So the idea was to try to combine things in one place to do the automated training. And the idea now is that we can start to do the training with the energy labeling, as well with the active learning that we implemented here with different strategies, and then we propagate dynamics. So this, the workflows using MLP train, try to combine the training aspect, labeling, with the training of the model, different architectures. And then also, once your model is trained, what do you do with MD? Can you run MD and what do you get out of that? So we implemented, we can run MD simulation with ASE, but also OpenMM. There are metadynamics with Plume. Plume is an amazing software to do metadynamics and to chain things around, so we can also connect to that. And either do right now kind of metadynamics during the training process or just as a way to explore other chemistry later. With OpenMM, there are work also being done by collaborators in Edinburgh that they have been implemented ML-MM approaches for that. Okay, and that is something that we're just starting to do with the hope of doing more biomolecular applications, but still early stages there. So what is our strategy for training MLPs? And for us has been very focused on applied strategy. We don't want to provide a model that will solve everything. We just want to provide a model that will do the chemistry that we want to explore, okay? And it will start with an example like SN2 reaction. Imagine that you want to get a model. For that, you have knowledge of what the transition state looks like. So you can get that from kind of AutoDE. And then your initial configuration, you have only one, but you can do random displacement of those. And like 0.5 angstrom, like you just distort the system 10 times, then you will have 10 initial configurations that will be used for training. So you label those 10 configurations and you start the training process. That will be the first cycle of training. And then you can do MD simulations. Your model will be very poor, maybe, but you can start improving that as you go on. Okay, so the days that you train your model, then you do sampling, and then you say, the model has to be improved. I will take new configurations based on a selector. I have this new data that I label, and then I train again the model. Okay, so that is the idea of the active learning approach. Before, people was using just putting all the data and doing nothing else, but now active learning is very common in many strategies. So you just start to add more data as you see you're testing the system on the fly. Is this good enough? Is this exploding? If that happened, do I have new configurations that I didn't know before? Maybe a proton transfer that I didn't thought that was possible. I can add that during the process. And our strategy early on was based on downhill dynamics because we often knew what the transition state was. We started from the TS, and as we were kind of propagating MD simulations with this new potential, we were going downhill. We're going downhill, getting new data points that were added into our system until we explored the whole energy surface. So that was the very early strategy. And the selector at that point was based on energies. Okay. Very standard in the field at that time was kind of, we get a new point, we check the energy. Is this energy very similar to anything that I had? If it's too similar, I remove that because I don't want to repeat data. If it's too different, maybe I don't want that because it's going crazy. It's doing some chemistry that I'm not interested on. Maybe I'm doing an SN2 and then I see something that is the CH bond is breaking. I just think, okay, no, this is too crazy. So then there is a criteria that you have to decide on what is the thresholds that you will allow the system to collect new data or to say, no, we're done. So often we propagate dynamics, and if our selectors say is removing like too many times, there is a point that you say, okay, I'm not collecting new data, I end this training because the new data is just as similar as the one that I have. The problem with this is that we had to compute DFT energies every time. So there were many cases that we compute the energy, say, oh, it's too similar, okay, it's removed. So we wasted this DFT calculation because we're not using that anymore. Okay. And that was the early stages. We did do some work and was already very interested to be able to do dynamics and study processes that were not possible with classical DFT models. And this is just one example. This is a trifurcation reaction where the idea is that you have a transition state that can lead to different products. And the kind of preference for a given product is not determined by the transition state itself, it's through dynamics later in the process. So there will be a bifurcating point after the transition state where that is determined. And of course, in DFT, you cannot do that because you just have a TS, and the TS will go downhill if you do intrinsic reaction coordinate just to one product. Cannot connect to two, okay? So, but with the MLPs, you can start to do that. You can introduce dynamics because that dynamics come from the process itself, the introducing temperature and so on. So in those cases, we have three potential products. This one being preferred experimentally, and we can propagate dynamics. And if you do ab initio MD, you can do the same. But often with ab initio MD, you can do maybe 100 trajectories, but going to 1,000 is very, very tricky. So at most, people was often doing 50 or 100. And you see that here, kind of, we need around 200 to start converting for this very small system. And with this, we were able to do dynamics, so we can see what is the preferred pathway. And sometimes we see the system going to one product or the other one as we propagate downhill. And what was very interesting here, that we tested different ML models, different hyperparameters, and so on. And the main difference actually was the level of theory that we were using for training. So it doesn't matter how fancy is your kind of ML architecture, if your ground truth value give you different kind of references, then your model will just give you that. We did test a bit relief because the original paper that we were comparing ab initio was with bit relief and MO6, but also did PVE that was very popular for the people using MLPs at that point. PVE is great for materials, but you see that give you actually the wrong preference. So most of the simulation were going to reactant, but actually the preference for the product was for the blue one rather than the red one. Okay. And with MO6, you see the same trend, just a bit of more a distribution between reactant and products as you propagate the dynamics. And then we also were looking at, okay, we were using active learning that was already speeding up our calculation, but you have this selector that is still very expensive. So Hanwen and Veronica started to explore different ways to select data without computing energies. And they implemented this similarity and distance-based descriptors. So I will describe a bit more here. So in the similarity, the idea is that we don't want to compute energy. So we know that we can use this SOAP descriptor, the smooth overlap, the atomic positions, where you have this molecule here can be represented as kind of densities around. And we can compute this kernel, the similarity kernel, and we'll say kind of how similar these molecules are. That we used to be using in GAP to get the energies, but we can use that as a different descriptor. And many people use SOAP independently for different ML applications, okay? And in our case, we wanted to compute this similarity kernel, where we have this representation of the new configuration, and then we compare that one to all the vector of the configurations that we already have in our system. And there are some parameters that we need to kind of take care of. So in that case, we will compute the similarity, and this is very quick. And then if we see the molecule is too similar, we just don't calculate DFT. We just calculate to the ones that are in our threshold. Okay, and those thresholds are very important because similarity kind of very kind of high. If the similarity is 1, it's telling us these systems are identical, okay, and we don't want that. So there are some thresholds that we want to define. But if it's too low, it will give us no physical structure. So if you go kind of below 0.6, probably will give you a completely different molecule, and you don't want that. So we have defined some criteria, so around kind of 0.9, that will give you the ability to sample those configurations. And that means that we only compute a DFT for those representations that are relevant for our training set. We also have the distance-based descriptor, where it's based on this local outlier factor. And this is very much used to identify outliers in a QM model, a standard model. So we have the point representations here of the available data, and we compute, okay, I have a new data. And how different is that related to the rest, kind of measured as an outlier too. So we also have some criteria to say what is the reasonable value here. And those things, like these two approaches are very quick. So either the SOAP descriptor in a kind of similarity, kernel-based representation, or this distance-based representation, okay? And you will see later that this we will use Maze today, and this is just a quick summary of the input data that we will use for training. So there will be a ways to define the selector that you will be using, but a lot of these different parameters, I will not go in detail through each of them, but will be kind of, I'm putting this here just to say kind of, there are many different things that you have to choose in the way that you represent your molecule, but also how much training you do. And the architecture is there, but the architecture has many hyperparameters that you need to define based on the chemistry that you want to explore. Okay, later Veronica and Howard will go with you through some of these representations. But just a quick points, like the cutoff is very important because imagine that if there are long range effects, where we usually compare, for example, if you do a very quick MD simulation, if you look at liquids, you see an RDF, a radial distribution function that give you an idea of how long range the interaction are and what is the kind of organization of your liquids based on that. And we use that information sometimes just as a quick way to say, okay, how far I have to go to describe our system. In principle, you want to have a very big cutoff, but that is very expensive. But also you don't want to have something too small that is kind of not describing this long range interaction. So in water, we know that there are two peaks, and then it's like, okay, I need to describe the first shell properly. I cannot have something smaller. So even with some quick MD, you can have some idea of the parameters that you will need to use for the radius, for example. So we have these two selectors, and how do they compare with the energy? So we have done a few tests with water, for example. And initially we're training a model just for water, very simple, with energy-based selectors, and then with the distance and the similarity. The numbers are not very clear, but for energy, to train a model that was kind of efficient, we needed around 280 configurations. If we use the similarity and the distance base, they are like around 40, 50 configurations. Okay? And what we saw actually, where we're using energy configuration, our new data were still very close to anything that was kind of the starting point. So they tended to be clustered around this energy difference, very small compared to the initial one. With the similarity and distance, we're able to sample the kind of chemical space much more smoothly with fewer data points. Okay. So that is what we have seen for this system, but also other organic molecules that we have been training. So both of them are very efficient and even better instead of efficiency compared to this energy. So now we need to compute energies for 50 points rather from those higher number, which already have some removed that they were useless, kind of that we couldn't use because they were too similar in energy, for example. So that is the relevance of using these different descriptors. So for us, the aspect of this using active learning and selector has been key to speed up the calculation. And the third ingredient of our strategy has been kind of enforcing and making good use of the locality of these models. MLPs by constructions are local. And for that reason, we started to think about kind of, can we provide information about the chemistry that we want to explore? So we saw that often people will do ab initio MD, where you have a box of water and one molecule of your reactants coming together, which means that a lot of the time you will be sampling very well water. You can have plenty of that, but not the chemical reactions that you wanted to do. So what we decided to do was exploring this reactivity, even in gas phase, just to account for the intrinsic reactivity and provide different data sets that will include solid-solvent interaction and solvent-solvent interaction. So the solvent-solvent interactions may be the more expensive, the bigger set, but actually we just need 50 configurations here, and we're able to focus on the interactions that needed to be learned independently. Okay? And that is the information that we combine. In this case, we're able to train this model for a Diels-Alder reaction in solvent. So the training configuration was only 600 data points, which is much cheaper than the other ones that we saw before, like 30,000 or 15,000 configurations. And the key was using kind of the efficiency of this approach was based on kind of using active learning, downhill kind of active learning, where we go from the TS downhill, and using these descriptors as well with the assumption of locality for designing our training data sets. So that was not something that came automatically, that was a lot of thinking. I kind of Veronica how and think of like, what is the chemistry that I want to teach the model? And once you train the model, you can do dynamics, but also you can do downhill dynamics here, where you can identify, very interesting, that when you have explicit solvent, you kind of have a pseudo intermediate. It's just staying there for a few femtoseconds and then goes to the product. But that's a kind of asymmetry of the reaction is just seen when we have explicit solvent. When you have implicit, it's much more symmetric and you don't have this kind of pseudo intermediate there. So here's just another representation of that. When you have, this is the transition state, and you have around 30 femtoseconds, a pseudo intermediate where you have a carbon-carbon bodies formed, and then the second one is formed later. So you have like kind of a range of 80 femtosecond difference. This is still very small, but show that this is asymmetries is more emphasized when you have explicit solvent. And the question came from reviewers also, kind of, okay, you're starting your sampling from the transition state. What happens if you don't know your transition state? And for that, what we decided to do is implement different training approach. So when we're doing the sampling, rather than starting the sampling for from the transition state and running dynamics downhill, we implemented the metadynamic or tempered metadynamics. So you can start from any point in the energy surface, and as you train the model, you explore new configurations, and then you pick up configurations that have been sampled through metadynamics. So rather than adding, there have been approaches that have used metadynamics in the ab initio of the steps. So just to collect data initially. In our case, we do that on the fly. So we start with a few data points, we do well-tempered metadynamics, and then we do that again. And what has been key is that we update these biases slowly as we go through the cycles. If you put new bias kind of from zero in every cycle, most likely your system will explode, especially in the very early stages when you have a potential that is not great. But if you do this inherited bias where you take the bias from the previous cycle, then you can sample more smoothly without issues with the system exploding, okay? MLPs have the same issues with force field. Any kind of small kind of, you have one data point that is bad in forces, and then your whole dynamics can go wrong. Okay, so that is very important to consider. And with that, we have been able to show this is a very simple system, SN2 again, but we can do either downhill sampling or well-tempered metadynamics. And in both cases, we can start from different parts of the energy surface, and we sample the energy surface, and we can do kind of get very similar accuracy. But what we see is that with the well-tempered metadynamics, we need more configurations because we are guiding less the system, but we have a much more smooth distributions of energies across the energy landscape. So downhill is very much focused on the transition state going down, so you sample that very well, but here you're doing that much more smoothly. And that may help more to the stability in the long term. That is something that is important to explore more. But in both cases, we show that they kind of both can give you an energy surface that is very similar to the reference path. And it's just later thinking about kind of the benefit of like in downhill, you really need to know the TS. Sometimes it's difficult to optimize. With well-tempered metadynamics, you can explore from any place and give you a better accuracy. And maybe something to test is stability later, because it's sampled much more smoothly the energy, homogeneously the energy surface. So this is around kind of the energies and errors in energies and forces that we care about. in MLPs, what we train during the training process, what we're doing is optimize a loss function. And the loss function is based in energies and forces. You can weight them a bit differently, but those are the key components. So you need to consider, people often say that the range of energy, mean absolute error, will be between 1 and 10. Even for chemical reactivity, we say kind of often 1 to 5 millielectron volt per atom is okay. After that, maybe the error is just too high. And forces are around between 50 and 150. And just as a reference, of course, the numbers are getting smaller as accuracy. Loss requirement for accuracy are getting higher. But to have something that doesn't explode and that seems reasonable, these are the ranges that we are looking at. When we compare, it's very important that we compare this error per atom, because as the system increases, error increases. So sometimes we often have in mind kcal per mole, but when we kind of try to compare the different works, it's not the whole error of the system, it's that per atom that we're looking at. And we have applied this same strategy to this system that is slightly more complex. It's a glycosylation reaction where you have an SN2 or SN1 pathway. And in our case, we started without knowledge of the transition state, and we did use the same strategy. Rather than training on this whole system, we have 3 different subsets. One is the gas phase configurations of the system. The other one is having a few solvent molecules, and the other one is just solvent molecules around there. So we have around 600 configurations here, and then we can train the model and combine them here. We also included later 6 out of equilibrium product state configurations because we are having higher errors on that. So you can just include them and then improve the model further. And then we can see the errors later across the potential energy surface, and also classify here reactant, intermediates that we found here, and the products. And you can see that the errors are kind of reasonable in our case. So it's smoothly sample around the different regions here. So this is the 2D energy surface that we can build with this model. And we see that the reaction is happening through a stepwise mechanism where you have an intermediate to here that is the most stable one, and then goes through a final transition state to get a product. Of course, these glycosylation reactions are very dependent on solvent, the nucleophile, and the leaving group. So you never know which path will be preferred, and there is quite a lot of experimental and QM data of the different options that you can have here. The other examples that we have been doing, and we're very interested, is metal complexes, thinking about later maybe metal enzymes. And Veronica did explore this for the first time in the group, looking at training a magnesium aqua complex. That is something that we will do later today, maybe just gas phase, but in this case, we did sample this one in water. Right? So many people, including myself, at some point did parameterized model for classical force fields, and there are many classical models for magnesium and other metals. And often what you rely is that you want to reproduce the solvation free energy and the geometry of an aqua complex. Okay? You parameterize your models, your van der Waals, and everything based on this description. Because with metals, you just have the +2 charge. So the only thing that you change in a force field is the van der Waals parameters. And the idea is that you want to reproduce the RDF and maybe the kinetic of the process of ligand exchange. And with classical models, RDF is very easy to get because you can really tune the model for that, but getting solvation or getting kinetic of the process is very difficult. Okay? So with just these small test sets, we're able to train a model that was stable here, was able to reproduce the RDF that we have, so the coordination number. So this is in gray is the RDF, and the integral of the first peak will give you the coordination number around. In this case, is 6. So it's very well defined because in water, you often have this very nice RDF. In organic solvents, they are less well defined. Often they are longer range, and you require a larger radius because of that. And we can reach maybe not very quantitative, but much closer agreement to experiment that using classical force fields for this dissociation of water in the process. In principle, we expect something to be symmetrical, and this is just the hysteresis that we have as we go from one side to the other, back and forth. But this is where we kind of very much interested in working into metal complexes and how we can train those efficiently. In particular, going away from water models. Veronica did palladium in acetonitrile. And in that case, we saw that kind of the cutoff and other parameters, they have to be better defined, and also the reference data that you use may need to be different. So this is just a kind of input set. Maybe it's very small here, but this is the input that we will use later today. So here you have the model that you are using. In this case, we're training a maze model. You have your system, so you provide the chart of the system, the coordinates, and then we will start. These are all parameters for the active learning training, and later for the propagation of the dynamics. So this is kind of the input that you use for training. It's very small if you're using then most of the other default parameters there. So the key things are kind of the input set, the active learning parameters, and then the MD simulation data. And in this case, it's just kind of an XCV comparison. You may want to do another reference data. And finally, very important and recent developments is as people have been introducing so-called foundational models. So always you have this, for example, you have force fields that are very general for any protein because they are based in these amino acids building blocks. In general, people have tried to reproduce, provide models that can be used for any type of chemistry. And that is a difficult task, but there are some models that have been trained in many different data sets. And this is just a summary to show two things. Materials community is way more advanced. They have many more data sets. They are much more organized in that area. And you have very large training sets here, developing in the last 2-3 years here. The main issue is that most of them are trained with PBE, which is great for materials, but it's not for reactivity. And this is just one example. For a simple SN2 reaction, if you do a PBE energy, this is the activation energy that you have. As expected, you don't have Hartree-Fock, so the energy is underestimated. If you include some Hartree-Fock with a component with DFT, or you go to a couple cluster, then this exchange will be included, and you have a higher activation energies. And we're able to train to that level of theory with MLPs. But that is showing that if you use any of these foundational models, one has to be aware of the reference data that you get. In molecules, people have been introducing more recently some. The most popular are the ANI models, and then the MACE of 23, which is training the SPICE dataset, kind of drug-like molecule datasets. And they are trained at a kind of a level of theory that is something that we will be using commonly for organic molecules reactivity. All of these models can be fine-tuned, and people is working actively in that area to identify ways to use these approaches. So you don't have to retrain the whole system. You can use this data set as a starting point, these models, and then fine-tune them for the chemistry that you want to do. And this is more or less where the community is now moving into that. And that is something very interesting, because if you think about the system that we were showing, in many cases we're doing solvent calculations, always the largest data set. Maybe those systems will know a bit more of the solvent, so I don't need to provide that information already. But it's important to know what are the data set trained on. So for example, MACE and P0 include a wide range of elements, but it's also much more complex to train, so may require more data, and that is something that if people is exploring too. The MACE of 23, we have used that as just as a force field out of the box for kind of doing energy optimizations, and that worked very well for organic molecules, okay? And even if you want to fine-tune that, it's relatively easy, because the chemical space that had to be learned, the complexity of the architecture is just kind of simpler. You just have 10 atom ties, while MACE MP0 has to be good at describing 89 atoms all at once, okay? So that is a bigger data set, but also includes some other elements, but also may require more information for learning the chemistry that you want to teach. So there are recent models that I just didn't add, but Meta has been introducing a new model there, and I feel that there are many communities developing this big data set, and for us chemists, now let's try to use them and push them to do things that are difficult. Just like the first idea was, okay, let's try to have models that are not exploding. And I think that we have reached that point, and that is great. That are giving us good geometries, and that is great too. So now you can use MACE just as a standard XTB in your workflow, and that will be very reasonable and way cheaper and better than a classical force field. But then can you do something better now, kind of be quantitative or push the system to see where is that exploding? Like people is working in those areas as well. So with that, just to summarize a few things, MLPs, I think that are very promising. We're very motivated to use them in chemical applications. So far, I was showing you type of toy model, but we're actively working on doing new chemistry. It's something that in materials has been used for a long time. So they are really kind of doing new science with these MLPs. We're still kind of developing the frameworks to do that, but I do hope that they will be a good solution to QMMM approaches that we're using currently, for example. However, reference data are very important. So even Meta and all the other ones are developing these fancy methods. You have to look at the chemistry that you're using. If you're doing excited state chemistry, you cannot expect to have a simple DFT to work. And people will say, oh yeah, I train a model. And then it's like people that are expert in that field, they will be kind of, oh, it's like with classical force field, you can always get something out there. If it's not exploding, you will get something. How accurate it is, it's very much the expertise that you have that will determine that. The locality aspect is something that we have been using is from construction because these MLPs are local, even though they're including a bit more long range effects in different ways now. But we use also them in the training. Something that I didn't mention much, but when we do the training, as you saw, I'm not giving any information about the charges. It's just energies that we provide. And now the new models are introducing kind of charges, dipoles, trying to account for this, provide some information about long range, or adding that at the top, like just indirectly. There are different approaches to do that. So that is another area of recent research to go beyond locality, but actually most of the chemistry that we see basically is very local. So that is the bulk, and it's very impressive that these local models can describe bulk properties as well. And then active learning and enhanced sampling is something that we're doing kind of, it's very obvious now, was not before, but that really improved. So combining selectors with active learning, it really speed up the way that we do the training so far. And there are many areas that we want to work on, transition metal complexes and some other system where we can really see where these approximations don't work. Maybe the locality is not enough, or maybe when we need to include charges or even spin. These are aspects that we cannot do currently kind of easily, and areas where people is working actively as well. And with that, I would like to, well, just thanks again, especially Howard and Veronica that are here that have been developing and leading the work in the area, but also people highlighted in bold are the ones that have been working since 2019 in this area. Many of them left, but have been contributing to MLP train and to developments that we have been doing in that area. And thanks to everyone for listening today.
Thank you, Fernanda. I'm pretty sure you have questions, but since we are a bit late, let's ask Fernanda during the coffee break and also in the afternoon session, in the hands-on session. Okay, so now we go to the coffee break and we are back at 20 to 12. So we have half an hour. Okay, break. Thank you. Also, we started. You were perfectly on time, but we see them.
Yeah, thank you.
How did it go? How did it go?
That's good. Yeah, otherwise it's very tiring.